Welcome to another coding challenge. In this coding challenge, I'm going to tackle diffusion-limited aggregation. So what is diffusion-limited aggregation? Well, I encourage you to take a look at two references. There's always, of course, a Wikipedia page. You can kind of find out a little bit about the history of this algorithm, how it was thought of, what it's applied to, what it kind of what it can be used for. The reference that I'm using here that I read right before making this video, or actually earlier this morning, a couple hours ago at this point, is a page on the internet from June 1991 written by Paul Bork, which describes the algorithm. You can see that diffusion describes, among other things, the diffusion of the aggregation of zinc ions in an electrolytic solution. Ooh, that sounds kind of exciting. But anyway, the point of what we can do with this algorithm is to create certain kinds of fractal-like, tree-like, crystal-like growth patterns, and you can see there's a variety of possibilities, and there's one down here that I particularly like, this one, which I might try to recreate by the end of this video. But let me, rather than read to you, as much as you might enjoy me just reading that webpage to you in this video, why don't I describe to you a little bit about how this algorithm works? At least how I think it works, and then the internet can always correct me. And once I start to write the code for it, we'll see if I'm thinking about it correctly. Because honestly, I don't know. I should have practiced this in advance. Something is definitely going to go wrong in this video. OK, so let's say we pick a point at the middle of the screen. And then we just say, oh, hello. I don't know who we're saying hello to. But there's this thing called a random walker. And the random walker starts here, just starts to randomly move around the screen. And at some point, it hits this point. Now, obviously, it's not going to take that exact path, although it could randomly. And once it hits an existing point, it gets stuck. And then we release a new random walker, and it starts to walk around. And when it hits an existing point, it also gets stuck. And then we release another random walker, and it gets stuck. And another one gets stuck, and another one gets stuck, and another one gets stuck. And as they get stuck, we start to see this fanning out pattern. So this is what I want to do. Now, I think it would be really interesting to actually animate the full process. There's kind of a spectrum here. We could write code to animate the whole thing, like we see these random walkers moving around the screen and getting stuck. We could also not animate anything and just see the final image. Or we could do something in between. I think I'm going to try to do point by point, but not animate the random walk itself. That's what I'm going to attempt. So let's go back over, and we need some code to start with, which I have here. No code. I mean, I have a P5.js sketch with a canvas and a background. And if I go back to the browser, I think I have it running here. In the browser, I can open up the console, which I'm definitely going to need for debugging. And so let's first start. What do I need? I think I want to have an object. No, you know what? Let's just start right now first. Let's do this rather simply. I'm going to say, I'm going to call the thing that's finished the tree. I don't know if that's a good name for it, but all of the points that are in the pattern, I'm going to call the tree. I'm going to need a walker, the point that's moving around. And that's just about it, really. And what I want to do is, and I need a size, like the radius for each one of these points, which, by the way, you could do it on a per pixel basis, so that always could be 1. But I'm going to try something like 16, just to have it be bigger to start with. So the first thing I'm going to do is I'm going to say tree index 0 equals create vector, a point in the middle of the window. And then what I'm going to do in draw is I'm going to say for all the points in the tree, say stroke weight r and stroke 255, and I'm just going to draw a point tree index I dot x, tree index I dot y. So and let's not worry about this walker for a second. So I'm going to refresh it. Well, OK, but I don't need to refresh it. It's live. I'm using this addendum package called live reload. So there's the point. OK, so now what I want to do is I want to create something that I'm going to call a walker. And I'm going to create it. I don't know if this is such a good idea, but I'm just going to put it completely randomly anywhere in the sketch window. It probably should start along the edge or something, or actually if you read Paul Bork's page, I remember now reading a point that you can make the algorithm more efficient by cleverly picking it close to where you think it might need to be. But I'm just going to create a random walker, and I'm going to see if that walker should be stuck. So first thing I need to do is check again all of the points of the tree, and I want to know the distance between that walker and a particular point in the tree. And if that distance is less than some threshold, r, I guess. Oh no, r times 2, right? Because I just want to know if those two circles are touching. So if the two circles are touching, the distance is less than twice their radius. If distance is less than r, then stuck equals true. So I'm going to create a Boolean variable, assuming stuck is false. And then I'm going to go through all of the points. And if stuck is true, I can say break. And now what do I do here? I'm going to say, and actually what I want to do is like keep going until you get stuck. So as long as you're not stuck, keep checking all of the points. And as soon as you get stuck, set stuck equal to true. And what happens if you get through this loop and you're still not stuck? Then walker should randomly walk by some amount. I could probably be more thoughtful about this. Walker.x should change and walker.y should change. The other thing I really need to do is I should make sure it stays on I don't want it to walk randomly far, far away off the window. So I should constrain it to between 0 and the width of the window. So let's see, and now, once it finds a point when it's stuck, then what do? I say tree.push walker. There we go. And now let's see what happens here. So I've got some infinite loop problem. This always happens. With live reload, I shouldn't be like, there we go. Oh, look at that. So I messed up. Something good is happening, but boy, did I mess something up. This is interesting. So I must have used an X and a Y. OK. That should help. Yeah. So interestingly enough, this doesn't look so totally crazy. Is this correct, though? Very hard to tell. So let's do a couple things. One is the stroke weight should really be half the radius. They should be right up against each other. Let's move it by just one thing I want to do is create. I'm gonna just make a random unit vector to be a little bit more controlled about how they're moving, and then I'm just going to say walker.add that velocity. So this is a little bit better, just to make a random vector and add that to the walker. I think this live reload thing doesn't work for me because okay, that's good. And actually, maybe I meant for this to be times 2. Yeah, there we go. Okay, so this is definitely looking kind of right now. The basic idea. Let's make this much smaller. Yeah. So you can see this is actually working, although it's quite of a slow algorithm. Can speed this up. So I think I've got the basics of the algorithm correct, actually. It's just kind of slow to do this one point at a time. Let's do it this way. One thing I want to do, wow, maybe this isn't as bad as I thought. Let's think about this. Let's do, I think we could release a bunch of walkers at a time. So let's try, releasing 10 walkers at a time. And just to see if we can kind of get this going a little bit faster. Oh, you know what? The walkers, I think, need to start from an outside point. Right? Well, let me do this, though, anyway. And then we're going to pick where the walkers start differently, which is going to be much better, I think. So, all right. So I just want to see something. I'm going to create a bunch of these walkers. And then now, actually, I can just do this as a loop, right? While you're not stuck. OK, if I'm back. And I thought of something which I think it might make a little bit more sense to be able to play with this a bit more by having the walker itself be an object. So I would like the, instead of just being a vector, I want it to be an object that can store both where it is on the screen, its size, I can call functions on it. That's going to give us more ways of playing with this algorithm and make it perhaps a bit more efficient. So let me go here, and what I'm going to do is I'm going to create a new file, and I'm going to call that file walker.js, and I'm going to make a walker object, a constructor function, and I'm going to say this dot position equals create vector, random width, random height. So I just want to take a lot of this functionality and that I've written out here, and I want to also, I want to create a variable called this dot stuck, and I want that variable to be false when it starts. I want to have a function that's called walk. So I want to, I want to have a function. I want to have a function called walk where I implement this algorithm where I pick a random vector, I add it to the walker so it moves somewhere on the screen. I constrain where it is in the window. And I want to have a function that says check. What's a better name for that function? Like update? No, stick. I can't think of a good name. Whatever. Check sticky. Check stuck. Whatever. That's going to be the name of the function. Check stuck. And in that function, what I'm going to do is I'm going to take this particular algorithm. And I am going to, and I actually kind of want to see them walk, but I think I have I actually kind of want to do this without the while loop. So what I want to, for a second, what I want to do is check all of the points on the tree and see if the distance between this walker's position, right, which is actually this dot pos now dot, right, the walker is now an object with a position, is near anything that's in the tree's position, because everything in the tree are walkers that are stuck. Oh, you know what I didn't do is I'm not delete. Anyway, so okay, keep. So, and then if it's stuck, I'm going to do something, obviously. Okay, so what I want to do here now is create an array of walkers. And actually, tree index 0 is going to be a new walker that is in the middle of the window, and that is stuck. So what I'm going to do in the object is I'm going to have some optional arguments. I'm going to say x, y, stuck, and I'm going to say x. I'm going to say x, or this is a way of doing optional arguments. So if I pass in an x, I'm going to create the vector at that x. But if I don't, x will be undefined, and I'll get a random value. Y or random height. Okay, and then same thing here. I'm going to say this stuck equals stuck, and if it's undefined, that's the same thing as saying false. And then I need to say, by the way, this dot stuck is true, and this is this dot pos, tree dot pos. Okay, and I should really check against some other array, like the others. I'll call that, which is called tree. So what I want to do right now is I want to create one walker in the tree, and then I want to create in the walkers, I want to put just a random walker. So I have tree and I have walkers, and I might as well do that the same way in index spot 0. And then what I want to do is I want to see, and you know what I should do is I should, now I can also have a function which is called this dot show, and I can actually take all this code. I should have done this at the beginning. I can take all this code and put it in the object. So I can set a stroke weight, set a stroke, and this dot pos, and draw the point at this dot pos dot y. And I could be a little smarter about this and actually just make this an ellipse. So I could be more precise about the radius, and I could say r times 2, r times 2, which is a global variable at some point, but I can have them be variable sizes at some point. Okay, so now I have this object. I have a walker object which can move. It can check to see if it's sticking to anything else in some other array, and it can also draw itself. So what I want to do first is I just want to say, let me display everything in the tree, and let me display everything in the walkers array. Okay, ready? So if I reload this sketch, walker is not defined. Sketch line 7, it's not defined because I have to remember to add a reference to it in my JavaScript file to walker.js. And missing walker.js line 25 has an error. So let me go down and see this dot ellipse, this dot pos.x, this dot pos.y. I don't see any error here on line 25. Oops, I had a period there, not a comma. There we go. Great. So I should see here, whoops, I should see this is this, and this is the walker. So let's just now in Sketch, let's also have walkers index I dot update. Oh, update was not it. Walk. So you can see there it is moving randomly. It's going to take a while to randomly intersect that. But it is walking randomly. I could obviously make it walk faster. So what I want to do now, actually, just as an experiment, is this is not at all, I've gone off the beaten path here from the actual probably algorithm. But I want to put 100 walkers into the space. Right? Okay, so they're all moving around randomly. And what I want for them to do is, if walkers index I check stuck others, then walkers, what I want to do is say walkers dot splice. I want to take it out of there, and I want to say tree dot push walkers index I. So I want to, what I want to do is I want to, anytime one of those walkers gets stuck, I want to put it in the tree, and I want to take it out of the walkers array because it's not something that's moving anymore. So let's check. This dot stuck equals true. So actually, let's make a function is stuck. Actually, so I don't need this variable. I can just say return true. And if it kind of gets to the end, return false. So let's look at that and see what happens. Others is not defined. Oh, tree, right? I have to pass in the tree. There we go. You can see them getting stuck. Go, go, walkers, go. Go, 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 walkers, go. So you can see how this takes a very long time. I'm kind of curious to try a few things. Let's try 1,000 walkers. And this isn't what Paul Bork describes what to do on the website at all, but I kind of like, and so I kind of want to highlight them differently. So I should actually, by the way, I should have that be a particular variable because what I would like to do when I draw them is if this dot stuck, I want to give them a different color. So let's so we can see which ones are stuck. So now, though, I think better than adding a ton. So let's still add it. Oh, let's actually do this particular algorithm multiple times per frame. Like, let's let it try to move all the walkers 100 times per frame. Why are they all clustering near each other? I'm drawing them 100 times. I don't want to do this show. So I just want to show them once. There we go. This is what I was sort of hoping to see. So now, there, finally. Okay, so now we can kind of see the algorithm happening, which I think is kind of interesting. It's kind of happened very slow. This is a complete and total brute force method. But I finally got something that I like here. And because at least it's sort of interesting to watch, it is happening kind of slowly. I want to try a few things to make it happen faster. Let's increase to 200 walkers. And let's increase the number of times to 250. The frame rate is a little bit slower now. I kind of like to keep the frame rate up. So let's go down to 200. There we go. So we could obviously, and the other thing I could do, it's interesting. Oh, it's slowing down over time. So the reason why it's slowing down over time is there's more distance checking. So one thing that I could do that would hopefully help this run a bit faster, which normally I wouldn't care about, but it is kind of bothering me how slow that it's running, is let's see if we can eliminate the square root calculation and to see if that makes it run a lot faster. So one thing that I'm doing here in the check stuck function is using this distance function. And I want to write my own distance function. I'm going to call it distance square. Euclidean distance, and I want it between two vectors, a and b. So what I want is the difference in x, which is bx minus a dot x. I want the difference in y, which is by minus a dot y. And now, normally, I would say return the square root of dx times dx plus dy times dy. This would be regular old-fashioned Euclidean distance, right? The square root of the hypotenuse of a triangle, a squared plus b squared equals c squared, or c equals the square root of a squared plus b squared. So what I actually want to do here is just write this algorithm, but take out the square root. And then what I can do now is not use this, but use my own distance squared function, and then I can actually have that distance be r times 4, which is what I want now is for the distance to be, did I mess something up here? Yeah, I'm missing a parentheses. What I want is the distance to be, instead of checking if the distance is less than r times r, I want the distance r squared, or r times 2 squared is r times 4. So this now, distance dist squared. This should hopefully be a lot faster. Wow, good. Okay, so boy, just eliminating that square root, you can see how much faster this is now. Okay, now here's the other thing: is every time I remove a walker, this is kind of nice actually, just to let it grow with a fixed number of walkers. I'm kind of enjoying that. There was a technical glitch there, but hopefully you're still seeing me. I see myself again. So you can see here that I have this kind of nice finished pattern, which I really quite like, actually. So some other things that I can do here are, one is whenever I remove a walker, I could say I always want to have 200 walkers. So I can always say while walkers.length is less than 200, walkers.push new walker. So this is, even when they get stuck, I add new walkers. So I never, and by the way, I started with, so let's make a variable called max walkers equals 200. And we're going to start with, we're going to do it, no, that's a different value. Max walkers, I kind of made, and then I'm going to make another variable, which is iterations, which I'm also going to make 200. Let's make these variables, I think, is kind of nice. Right? And we can see how it behaves, So now I'm always keeping 200 walkers. So I want this really to happen pretty fast. So let's see if I can up the iterations a bit. and see if we can get this screen. Now, it is sort of slowing down. So I think we're in pretty good shape. Now, here's the thing. I think what's interesting, oh, you can see it really slowing down. So if I go back to, oh, and you know what? There's also a problem here, which is that I shouldn't be creating random walkers anywhere in the window. I should only be creating them around the edges. So let's also make that improvement, okay? I think it's worth making that improvement. So I'm going to go back into the walker, and instead of doing random width, random height, I need a function. Let's do a random point, and I'm going to give it that x and y. Right? I want to have some separate function somewhere that's going to take care of this for me. Actually, I'm going to say if x, this dot pos equals create vector at that x and y. So if you get an x and a y, otherwise, let's pick a random point. Now, I'm sure there are lots of clever ways I could write a function to give me a random point along the edge. But the way I'm going to do it is as follows. I want 4 possibilities: top, right, bottom, or left. So if I'm picking something along the top, I want a random x, and I want to return create vector that random x comma 0. Else if I equals 1, let's just say that's the bottom. And again, we could make this more efficient. Let's make that along the height. Else if I equals 2, I want a random y. And I'm going to along the left side. And in all other cases, I want a random point along the right-hand side. So let's run this now. You can see that I'm only picking random points that are coming from the edge, which I think is also going to work a lot better because I don't want to pick random points kind of inside the thing that I'm already creating. So here we have now diffusion-limited aggregation. Go, go, go. I wanted to finish. So one thing that I kind of miss, so this I got to come up with a clever solution to figure out when it's done. Because you can see it's kind of, it's now like just infinitely picking points along the edge, and it kind of went crazy a little bit when it kind of got to the edge. So, but I kind of like the idea of actually, just for right now, not adding any more walkers and starting with a fixed number of points. So I'm going to start with 1,000 points. And yes, it is running kind of slow, but when those points are removed, we got to get our first point to get stuck randomly. There we go. I think it's going to kind of speed up over time, is my belief. But and you know, one thing I could probably do, which might also help it run faster, is draw less stuff. Or what might be better is to just add 1 point at a time. So I think really the way that you would do this is let's just do 5. But have 1,000 iterations. Here's another way to doing it. Yeah, I like this. This is nice. Oh, I like looking at it this way too. So there's so many different ways we can visualize this. I'm kind of stuck on it. And I encourage you to sort of enjoy coming up with ideas on your own. But what I do want to do is, let's go back to this. What I do want to do is kind of look at how you can vary this algorithm to get different kinds of patterns. So let's go back and look at the Paul Bork website, and let's first sort of see a couple things. One is, right now this is essentially what I'm getting. I could do a better job of kind of thinking about the layout of the space and making the algorithm more efficient, or letting it run for a long time. I encourage you to do all that. I'm going to release a processing version of this, which maybe runs for a while and renders the final version to an image. Somebody remind me in the comments if that doesn't exist, so we can make a version of it that looks like this. In the browser, it'll kind of, I don't want to shut down a browser window, but let's at least first let's try to see how would we create this pattern. So this pattern, it's all about the seed points. What if I fill the tree with points along the bottom? So let's let's fill in the beginning, instead of having one point, what if I say for var I equals, I'm going to say var x equals 0, x is less than width, x plus equals r times 2. And what I want to do is say tree.push new walker at x comma height. So I just want to create a whole bunch of points that I start with at the bottom. And you can see what happens when I do that. Now, what if I think I want all my walkers actually just to start at the top. So let's go now to the walker file. And what if I basically say, you know what, let's just always have, I'm going to comment all this out, and let's always have all the walkers start at the top. So I just changed this function, have all the walkers start at the top. Whoa. What did I do wrong? I'm back. There was a major problem with my code, which is right here. Remember how I was saying I'm so clever, and I can check to see if the user gives it an x and a y. So if there's an x and a y, make a vector out of the x and the y, otherwise make a random point. Well, it turns out that if you give it the value 0, right, 0 evaluates to false. So when I say make a walker at 0, 0, for example, or 0, height, it's actually going to not make it at that point, but give me a random point. So what I actually need to do here is say, as long as x is not undefined, and I'm sure there's a more elegant way of doing this, but I'm just going to fix it right now and saying, and y is not undefined, do this. And that should, I think I have some sort of browser having crashed problem. Infinite loop problem. And also, I think I can do away with this third argument stuck and just say this dot, you know, it's if I'm making it at a particular point, it's automatically stuck. Otherwise, it's automatically not stuck. Just to be clear about that. And now we should see, okay, so here we go. Now we have starting all the points at the top, and they're going to kind of get glued at the bottom. So this, we should see some kind of pattern as this runs for a little bit. You know, speed ahead in this video if you want. You know, listen to some music while you're waiting. Come on, trees, grow. So we should see a pattern that's coming much more like what we've got here in, oops, I'm in the wrong place, what we've got here in this particular example. So here's another, so come up with your own scenario. What if you start with points all along the edges? What if you start with points along a radial path in a circle, or have points moving, you have points starting around the edges of the circle and your random walkers all start in the center. You can get something like this. Now, but I do want to add something else here, which is, whoops. I got too much music playing. Okay, I do want to add something else here. Let's just see how it's going. You can see, it's moving along here. We're growing our trees. I want to go back to Paul Bork's site, and you can see something here which is interesting. Look at this particular image. Now as I scroll down, look at this particular image, and look at this particular image. There's a kind of density or fuzziness or almost hairiness to it. And what you can actually do is, it's called stickiness. You can have a probability. You can think of when it touches something that's part of the part of this tree, this diffusion-limited aggregation thing that's growing, you could have a probability that it gets stuck rather than automatically getting stuck. So I think that's something interesting to add. For example, if it's within this threshold, don't just automatically have it get stuck, but pick a random number between 0 and 1. And if that random number, like our stickiness is now 10%, then I could actually have it get stuck. And unfortunately, we didn't get to see how that was going. Let me see if I can make this run a little faster. There's a couple things. So I'm gonna give it more iterations and more random walkers. The other thing that I could do actually that I think would really help is I could have the walkers as they walk, not just, I could have them only ever walk down. So I could actually say, I'm just going to comment this out. Var velocity equals create vector, some random amount between -1 and 1, and then some random amount between 0 and 1, so that these the random walkers only ever move down. Boy, they move down much too fast. I guess maybe I should wait it just a little bit. Something like that. Oh, okay, hold on, too many. This was a nice idea that I had that doesn't seem to be working out very well. There, you can sort of see, I don't know if this was a good idea or not, but you can sort of see how if I have them randomly moving down, why do they always go back up to the top? I'm adding them back in again. That's making it run slower. So yeah, so I wanted to take that out actually. And you can sort of see, anyway, you can see that by varying lots of the algorithm. When I publish the code for this, I'm going to make you a nice clean version that works really well. Because there's so many variables you can play with here. Okay, I want to play with one last variable. So look how slowly, like, come fall walkers, go to the bottom, stick to the aggregation pattern. Oh, okay, so let's do one last thing. What I'm going to do now, which I think will be particularly interesting, and, is try to recreate this pattern. Notice how the walkers at the center are larger than the ones on the outside. You can see this one as well. I didn't get to do didn't get to see the probability thing play out. Let me take that out for a second. And so what I want to do now, before I leave you, if you're still watching, is I don't want to have R as a global variable anymore. I want to have each walker have its own variable. So I'm going to make R 32. And I need to look for anywhere that I reference it, this.R, other.R. Right now I'm also importantly checking my own radius against another radius, or others index I.R. And then I also want to draw it with this.R, this.R. So one thing that I could do, which is, and then I want to go back to the center, the version where it's where it's starting in the center, which I think is a bit easier to kind of work with right now. So I'm going to take out this tree that starts off the bottom. Let's just make sure this still works. Whoa, look at these. So if I make them really quite big, that was kind of interesting. Let's make this 8. Okay, so you can see what this looks like now, and this is working again now with just sort of larger circles. And I kind of would like to, just also when I draw them, I would like to give it a little bit of alpha here, I think would be worth seeing. Let's, just a little bit of alpha. Okay. So now we have the basic core algorithm happening, and you can see all of these walkers getting stuck. So what I want to do, I think, which I think would be interesting, is I'm gonna make the maximum number of walkers just 10, but I'm going to increase the iterations by 10 to 1,000. So these are the walkers now sticking one at a time. Now there are only 10 of them, so 10 of them are going to get stuck. That's all we're going to see. But now what I'm going to do is I'm going to, each time I delete one from the array, I am going to add a new one with a smaller radius. So what I want to do is let me get the radius of the last one in the array. This might be and I'm going to make a new walker with, oh boy, I want to make a new walker with that radius times 0.5, so half the size. The problem is now I need to make the walker be able to be created now with a radius, but at a random point. So I think one thing I need to do, one thing I could do actually, this is better, is I could say if arguments.length equals 2, that means I've gotten 2 arguments in x and a y, then create a walker with a radius of 8. Otherwise, then create it with the radius of, and then otherwise if, otherwise create the walker with the radius of the first argument. So if you have less than 2 arguments, so this is another way I could just check that arguments array. I have a video tutorial about that. Otherwise, I can make one with a particular radius. And so let's see what happens here. Okay, so where am I making walkers? So this is with I forgot. No. So with wait, or else if arguments dot length equals 1, else now with no arguments, right? Then the position is random, the radius is 8, and stuck is false. So now the other thing, whoa, what just happened here? Back, I realize there's a problem here where I'm passing it 3 arguments because I had an extra stray true from before. So let me take that out. And you can see this is working now. Strangely enough, though, the walkers are getting like really small, really fast. And I just realized that's because what I want to do is get that, before I start adding a whole bunch of them, I want to get the radius of the last one there. Because when I add one and get the radius of the last one, they're getting smaller and smaller. And let's just make them go down by 75%. So you can see here that the walkers are getting smaller as they add them back in. And maybe that's like too much. They just get smaller so quickly. So let's see what this does. Yeah. So you can see over time, as I'm adding more and more walkers in, they're getting smaller and smaller and smaller. We could also do something now while we're here. Let that run for a little bit. Let's see if I give it 50 at a time. Will it kind of perform okay? So one thing that I want to do is, and I actually could just have every walker in sequence be actually a little bit smaller than the previous one. That might actually be a better way to do it, because I could have like a radius counter, and that's kind of, yeah, let's do it that way actually. Let's try this. I want to have a radius, a starting radius. I can actually just say radius equals I can have a starting radius just for that center one. No, that's fine. Radius. So I want to have a starting radius of 8. And whenever I make a walker, I say radius times equals 0.99. So shrink it a little bit. Shrink it a little bit. And then there's another place where I make new ones, which is here. Shrink it a little bit. And then actually, I can take out this idea of the argument, because I'm just going to use a global variable. I don't love this anymore. I'm just use a global variable, radius, that's always shrinking, to go back and put that in here, and have this always be radius. So there is only back. Now I'm sort of simplified back to just 2 cases. I either am getting an x and a y, and this .r is always just equal to that global variable. I don't like now how I've done this, but we're going to do it this way anyway. So you can see every single one is like 1% smaller than the previous one, which is kind of interesting because we're getting sort of, they're actually not exactly in order. So that's not what I intended to happen, but we are seeing sort of an interesting result from this, and they're getting smaller and smaller and smaller. And then I could also say, what I like about this is I now have sort of like a terminal point where I can say if the radius is less than 1, only bother to do this if radius is greater than 2. So now we actually, like, I don't want to have circles where the radius is less than 1. So now we actually have a terminal condition for this algorithm. And I also now want to add one last thing, which is coloring them. So, I could actually, so the other thing we could do is I could have I could map their hue. So I could say, color mode, HSB, and in the walker object itself, got to add this in. I could say fill. I could say the hue is mapped to the radius, which goes kind of between like 0 and 8 to between 0 and 360, and I could give it that color. And I think I'm actually going to say no stroke. And let's forget about the coloring it based on whether it's stuck or not. And I have an error somewhere. So we can see now, and they're not actually, so I probably should order their color based on when they get stuck. But this is kind of interesting nonetheless, and you can see as they're getting smaller and bigger. And you know, I don't know why it just stopped right there. Oops. But you can see I'm going to clean up this code and give you a working version. I might change the order around the colors. I'm going to, I'm very good at crashing Chrome, but you can see sort of the ideas behind this particular algorithm. I don't really, my time is up, I think, because this has gone on for way too long. I don't have a good, perfect version of this to show you, but I will include that in the link from this video to the source code. I'm going to make both a P5.js and a processing version of this, so I can do kind of like a higher resolution one that kind of generates it and just saves it to like a JPEG, so you can see how that works. Maybe I'll come back and do another video follow-up about that. But now you can see sort of the basic idea and the implementation behind this particular algorithm that's on Paul Bork's website. Okay, thank you for watching. And I'll see you in another coding challenge soon. Back for a quick addendum. I kind of cleaned up the code a little bit and it's making it work a little better now. I had two big things that I missed. One is that it was crashing the browser. I think I need to point this out because I had this while loop that was always trying to fill it. I was trying to fill it if it ever got less than a certain amount, but I didn't allow myself to add any if radius was below a certain amount. So it got stuck in that while loop. So I fixed it to just say only do the while loop if radius is greater than 1. And the other thing that I did is I added a hue variable so that each time it gets stuck, I increase this sort of global hue variable. And you can see now the hue is sort of assigned to the order in which it gets stuck. So this doesn't exactly match what you see on these particular scenarios, but I bet you with a little bit fiddling and tweaking of the algorithm, you could get something like that. So give that a try, and as you make more beautiful and interesting versions of this, think about ways of optimizing it, of where you start the walkers, how many you use, how you check to see if they're near something. We'll come back and I'll make some improvements to this, okay? This is really the end now. Goodbye.